Well, hello and welcome to Codebase Alpha. This is episode 79, and we're going to continue with what I'm calling Project Z this evening. So this is the project to create an accurate Z80 emulation. The Z80 being an 8-bit processor from back in the day. It's still around. I think they still use them, but it was actually the basis of a number of microcomputer systems back in the day. And one in particular was the ZX Spectrum. There was also the Amstrad CPC, and a number of other machines, a Tandy, I think, as well. And so the plan for the project really is to create this Z80 emulation and package it up as a NuGet package, and then make it available through NuGet, freely available to anyone who wants to use it. But as a kind of a sample application or implementation, we're actually using it to emulate to more or less a degree a ZX Spectrum, and we're going to see how far we've got with that this evening. So I think Pops, it's best if we drop over into the code quickly and see what we can see. So let's go into our coding scene. There we go. Okay, so last time, last Monday, we had our emulation, Spectrum emulation running like this. So we started up and it kind of stopped here, and that was what we got. And I was, to be honest, pretty pleased that we managed to get some screen output. So we got the boot screen for the ZX Spectrum, which simply is this copyright statement. But now what happens if I press any key on my keyboard, on PC keyboard, we now get a flashing K. Now, this is really interesting to me, is that you imagine you're bringing your brand new Spectrum home, plugging it into your TV, hooking up your cassette player, switching it on, pressing a key, and that's what you get, a flashing letter K. And I guess people may have expected it or knew what it was all about, but when I first saw this, thinking, wow, what on earth is that all about? But as you see, what we have here, we have a couple of features. We got some. I pressed a key and it did something, and also we got this this blinking effect. So I'm not going to show you any more of this just now. We'll shut the emulation down, and we'll talk about the keyboard. So here's in the code here. This is in the SMB Spectrum 48 project here, which is our kind of little sample implementation. We have an image of the Spectrum keyboard, and it's rather crowded. This was one of those kind of rubberized keyboards, a bit like the keys on a calculator, the rubber kind of keys. And you can see it's absolutely crammed with text. So not only is there a standard kind of QWERTY layout, but each of those keys has a kind of a function in green, which is in this case for the Q here, it's the sign function. It's also got something in red below, which is ASN. It's got a keyword, plot, and it's also got less than or equal to. So there's a whole combination of kind of keys and different kind of input modes, which were used on the Spectrum to actually input text or input entire keywords. So we'll look at that. So what I'd like to do first is to kind of explain to you how the Spectrum keyboard actually works in terms of what inputs, when you press a key, what inputs happen. Let's drop over to OneNote, and I'll scroll down. We'll try and sketch out what the keyboard actually looks like under the covers, or what kind of conceptually. So basically, it's a matrix. We have, if I write across here, bits, bit 0. Oops. And there we go. So this is bit 0, 1, bit 2, 3, 4, 7. So those are your kind of 8 bits for your Snowball. Welcome to the stream. Good to see you. Do I have a Codebase up a monochrome logo? I don't have a monochrome on. I just have the kind of the blue and black. the A, letter A, which I can let you have. That's not a problem. But it's basically blue and black. I think maybe might have some white lettering. Okay, so those are the 8 bits in a byte. So these kind of form the columns that we're going to have, and then there are 8 rows. In fact, these bits here aren't used. We can say not used. We're looking for input for the upcoming shader stream. So yes, Fuel Stable and I are planning on a new shader stream. Hopefully next week, if we can match the diaries up. We're going back into the world of 2D shaders, I believe. Is that right, Fuel Stable? So yeah. So as I was saying, you have these 5 bits here, from the least significant bit up to bit 4, are what we use to determine a key press. And then we have 8 rows. So each of these 5, if we go back to the image here, you can see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 keys per row, and there's 4 rows. What we're going to split this into half rows. We're going to say half rows. So we're going to say this is 1 row, and this is second row, row 3, row 4, etc. So these keys, up say 1 to 5, are 1 row on what I'm describing at the moment. And there's 8 individual rows, and the rows are kind of numbered rather strangely. So I'm going to label this value B, and I'll tell you exactly why it's called B in a second. And basically, the row is indicated by having a 0 in the bit position that the row relates to. And that's easy to show you than explain. So I have 1 1 1 1 1 1 1 0. So this 0 here obviously is in bit position 0. This is row 0, or the first row. And then all we do is move that 0 along each row. Here's the second row, third row, fourth row, etc. And then each of these bit positions in the over here relate to an actual key. So this is this first one is shift. So 1 there is a Z. This is an X. One is a C, and this one is a V. And then we've got an A, S, D, an F, and a G. And then we've got 1, 5, and then 0, 8, 7, 6, and it goes on. Okay, so how this actually works is that if I was to press, for example, the A key, when the keyboard polling process was scanning this row, so we're scanning this row here, if the A key was pressed when we scanned, it would output a 0 at that position. That would be a 0, and the other ones would be a 1. So 1 means the key is not pressed, and a 0 means the key has been pressed. And we scan through these separate rows, and we can actually press 2 or 3 keys at the same time and pick it up. So it's like a cross matrix. So we got almost like wires going across, wires going down, like this, and where the key is pressed, we get a 0 that's produced. So for example, on the A key, we'd get a 0 produced at that position. So that's what we have to kind of interpret. And I mentioned there's a keyboard scanning routine, and that's kind of fundamental really. In the 16K ROM that we've got loaded up for our emulation, that is a keyboard scanning routine, and it's tied in to what's called an interrupt. So what an interrupt is, there's 2 different types of interrupt. There's maskable and non-maskable, and we're talking here about the maskable interrupts. And a maskable interrupt simply means that you can, as a programmer, disable it and then re-enable it so it doesn't happen. So what happens within the spectrum is that we need to be able to call the maskable interrupt routine 50 times a second, every 50 times a second, or 50 hertz, every 0.02 seconds. We need to call that interrupt routine. And what happens then is that as part of that routine, it does other things as well, but part of that routine, it will scan the keyboard. It will poll each of the 8 half rows and say, have you got a key pressed? Tell me what keys are pressed on those rows. And then it will interpret those key presses and produce output on the screen, or at least that's what we hope. So let's go and have a look at the code that we've got for that. Okay. So you remember last time we had our screen that was being refreshed about 50 times a second. So we had a frame rate of about 50. So what I kind of guessed about what the formula might be for getting that kind of frequency of refresh on the screen, and I came up with I'm actually writing the screen in 3 thirds. So I'm writing the top row of each third at the same time, the second row of each third at the same time. So basically 64 writes, 64 running of my rendering program will just create the entire screen. Because the number of rows on a spectrum screen is 192 pixel rows. So divide that by 3, you get 64. So I know that we have to, in 0.02 of a second, we need to have written 64 kind of pixel rows. And so I divided 0.02 by 64, and I kind of figured, well, if I allocate 80% of that time slice to the CPU running CPU commands, and 20% of that time for the renderer to read the video RAM and to actually create the screen, and then to produce it and copy it from its buffer across onto the actual onto our screen, then that kind of might be right. Then we can tweak this at this 0.8, this 80% figure. This sort of formula here, it's a static formula. So we multiplied by the stopwatch frequency, here, which for me is 10 million ticks per second, and that gives me a number of stopwatch ticks that I have to play with in terms of running my CPU. So once I've exhausted this number of ticks, then I run the renderer. Now this isn't really ideal, because what I'm getting through from my on-update method here is passing in the number of seconds elapsed in the last time it went through on update. So this is kind of giving me a real-time figure. So how long did the last pass through the on-update method take? And I really should be able to use that in a formula. So this is dynamic. So if I hit a particularly kind of process-heavy section of code, then it should be able to compensate by reducing the number of CPU cycles in the next run of on update. But I haven't really managed to get us anything satisfactory. I can kind of put guesstimates in, and it kind of works. But this formula actually gives the best results, most stable results on my computer. So if you do download this piece of code, and you may need to tune this figure, this 0.8. The 80% kind of rule there. I would like to try and figure out how to use the elapsed time, so that if the elapsed time is shorter, then it's going to give a greater number of ticks to the CPU, and if the elapsed time is longer, it's going to give fewer ticks to the CPU, and that way it should kind of average out to be about 50 frames a second. I haven't done that. I've had a quick go at it, but I was kind of more interested in doing some of the other things I'll show you on the stream this evening. But if anyone feels like having a go at working what that kind of formula could be, do feel free to submit a pull request, because I'm well up for that. So actually, I'm missing some music. Let's get some music going. There we go, a bit of Relax Daily. So that's that. So we've now got something here, which at least on my machine is outputting screen updates at about 50 Hertz. And if you remember last time, what happens is basically come down to here. Basically, if the screen's not ready, then we run the renderer, and then we kind of cycle through CPU steps, and then if we drop out of this, we go round and again, and then eventually screen ready will be true. When the screen is ready to be shown, we'll drop through here, and we'll actually basically do this draw sprite method, where we kind of get the buffered sprite, which represents the screen, and flash it onto the actual video. So if you're not familiar with what we're using here, this is something called the Pixel Game Engine. Really, I use this to save me having to write loads of kind of code for dealing with graphics. I'm not really a front-end developer, so I wanted to find a shortcut for having to write all that kind of stuff. And this is Pixel Game Engine is something that's been written by Javid X9. I don't know who Javid X9. He does some fantastic stuff in C++. I'll just give him a shout out, Javid X9. I do catch his streams and also his YouTube channel. This actual implementation, C# was done by someone called Dev Chrome. And I don't know much about Dev Chrome other than he did this. So Fieldsnapper says, didn't listen to that well in doing other things. That's fine. You couldn't assign a budget of cycles that allowed the emulator, so the interrupt handler steps. No, it's the other way around. So what I've done, Fieldsnapper, is I kind of worked out empirically how many ticks of a stopwatch would give me approximately 50 frames per second output. And this render ticks is the number of ticks that have to elapse between renderings of 1/64th of the screen. So that's why the 64 number's in there. So if you remember, we draw 1/64th of the screen each time we run the renderer. So that's 192 lines of pixel lines on the screen. And so I use this, and here basically I say if the elapsed ticks is less than render ticks, and we haven't got a screen that's already ready, then just go into a while loop and run the CPU steps. It's not particularly accurate, because a CPU step can take anywhere between, say, 4 ticks of the or 4 CPU cycles at 3.5 megahertz, and it can take 20, 25, or even 29 of those. So using a step is a vast oversimplification. What we should be doing is counting CPU clock cycles, but I'm not doing that, because the purpose of the project wasn't to create a Spectrum emulator. That was kind of a bit of the output, the kind of bonus output that we get from the project. The project actually is the actual emulator itself, and that you can make your actual machine emulator as complicated as you want. So this assumes that the emulator is faster than the original CPU. Yeah, it is faster. I'm trying to kind of to limit it, but to be honest, the resolution of a stopwatch tick isn't really good enough to have a very accurate slowing down of the actual running of the emulated CPU. The interrupt does run at approximately 50 frames a second, and that's good enough for what I'm going to show you, and you'll see. Okay. So what we do when we do the run renderer here, the step renderer basically, as I say, draws the one row in the top third, one row in the middle third, and one row in the bottom third of the screen each time it's called. So a step renderer basically produces 3 pixel lines on the screen, in the screen buffer, once that's been through 64 times, it's going to set the screen ready to true and up the frame counter. Okay, so then when it comes back here, if the screen ready is true, we're going to actually set interrupt to true as well. So this is going to be the approximate 50 Hertz maskable interrupt. The stopwatch can time individual instructions. No, it can't. There are APIs, are there, to detect how many CPU cycles you spent. That's interesting. And we are running here multi-threaded, obviously, because the game loop is running in one thread, and then that's interesting that we can do that. So maybe things we can do. So once again, invitations are open if people want to have a play, submit some PRs. Quite happy to have that a good, accurate way of making the CPU run at the correct frequency. Great, thank you for your snap. That'd be really, very helpful. But at the moment, it's not that much of a problem that the CPU runs faster. The emulated CPU runs faster than the real thing, and you'll see it's not that much of a problem. It's a bit of a problem in some circumstances, but most of the case it doesn't actually matter. So by setting the interrupt to true here, that means that 50 times a second that flag will be set to true, and our Z80 emulation code is actually looking for that value to be true. And when it is true, it runs our interrupt routines, and I'll show you that kind of code in the emulation shortly. The other thing we do on the Spectrum, the ZX Spectrum, there's only really two interrupt modes are used. Interrupt mode 0 is never used on the Spectrum. We only use mode 1, which is the simplest mode. Basically, interrupt mode 1 means jump to a specific location in the ROM and execute whatever you find there. Then there's interrupt mode 2. Interrupt mode 2 is quite complex in that with it you can create what they call a vector table, or many vector tables. So individual devices can call an interrupt and say, oh, here's an offset into a vector table, and that way it can do very specific device dependent interrupt routines. However, on the Spectrum, that's actually the way it's worked, because it basically it boils down to a couple of chips. There's the CPU and a thing called the ULA, which is why the architecture is so simple. There's only really two components apart from your RAM. That can't really because it's a single peripheral device in many ways. It can't actually produce the data to say go to particular locations or go to particular entries in a vector table. So all we do is return FF in this case. So if we're in interrupt mode 2, we're always going to have FF as our offset on the vector table, and that you'll get to understand that a bit more when I show you the code for the interrupts. Okay, so that's going to generate our 50 Hertz maskable interrupt. 50 times a second, it's going to jump to the interrupt routine, and it's going to execute whatever codes it finds there. What is at that location? Well, there's a whole load of stuff, but one of the things there is a keyboard scanning routine. So what it's going to do, it's going to scan through each of the half rows of the keyboard matrix looking for depressed keys. So if you're Snobby, you say that you sent me a link and that say that modern CPUs vary in frequency. Yeah, yes. I would like to have a good way of setting the timing of the CPU up so that it takes the right length of time. At the moment, I don't think I've got a very good way of doing that, but it doesn't actually interfere with what we're doing. As we kind of build the emulation and work on the really kind of nuts and bolts under the covers of the emulation, we may have to get something better. Okay, so what happens when an interrupt an interrupt happens on the CPU. Let's go over to the Z80 file. Down here we have the interrupt. So whenever we've completed a step, we call handle interrupts, and you can see that it handles the non-maskable interrupt first and then the maskable interrupt. Now I've done nothing with non-maskable interrupts, so if any of the software that we're going to test out tonight actually uses it, I'm not generating one from my emulation, so that may account for some glitches and oddities. However, we are running this interrupt. What we do, the first thing, if our CPU is halted, i.e. we sat there waiting for an interrupt to happen, we unhalt the CPU, advance the program counter, and then carry on with the program. That's quite an important thing. One of the reasons why we've got a halt opcode in our kind of instruction list is so that we can wait for interrupts. We can sit there doing nothing, waiting for an interrupt to happen. And that's why you can kind of sit there waiting for a key to be pressed, and we'll see that. So then we have a switch statement based upon the interrupt mode. Interrupt mode 0 is where you can pass in on that data attribute. You can pass in any instruction into the CPU to actually run. However, I'm not quite sure how to do any instruction. All I've implemented so far is the two most common instructions which a peripheral device might send, and that is the RST, which is basically jump to a particular location on page 0 of memory and execute whatever you find there, or a call, which is a call to a subroutine. Okay, so interrupt mode 0 is not used on the ZX Spectrum, so we can kind of forget about that from the point of view of this evening's kind of investigation into the code. Phil says, I think my thinking about an emulator with precise timing, I suspect you start a vertical blank. Most games are oriented around vertical blank. Yes, vertical blanks, absolutely. You're absolutely 100% correct. So a lot of games actually were written so that during the vertical blank, which is where the remember this, we're going back to kind of the 1980s here. We've got a cathode ray tube, so there's an electron gun which is scanning across the screen, firing electrons at a phosphorescent screen. They actually go well below the visible part of the screen, and they actually scan lines which can't be seen. This is called the vertical blank. And a lot of games, for example, will be written so that while the electron gun is scanning the vertical blank, either there's nothing visible on the screen, then there's a lot of calculations which can change the screen, so you don't get kind of flickering and blinking. And what we'll see on my emulation is that when we get to doing some graphics, then there is kind of flicker. I'm not sure whether you've got the flicker on a real Spectrum or not. I suspect probably not, but my emulation of the Spectrum isn't perfect. But as I keep saying, that's not the object of the exercise. It's the Z80 emulation which is the object of the exercise. What we get out of it in terms of playing around with a little Spectrum emulator is kind of the payoff, which proves that it's kind of working. Okay, so interrupt mode 1 and 2 are the ones which the Spectrum uses. Interrupt mode 1 is the common one. Just as on MSX, you switch the attributes per raster line. Get more precise. Yes, I do scan. I scan the attributes, which is the colours, for every line. Yes, not just for every character. So hopefully it's kind of more precise image. Interrupt mode 1, which is the most common, simply jumps to whatever routines at 0038 in the ROM and executes it. And that is basically where standard kind of keyboard polling routines live. And that's what, on the whole, when we're programming in BASIC, for example, we're in interrupt mode 1, and it's a simple, we press a key, the keyboard scanning routine picks it up. But it's, as you can see, it's fixed. There's no room for us to change this code. We can go in and change it, but really, if we go and change this code, we're kind of in dangerous waters. What we want to be able to do is to send the CPU to an area in high memory, not in the ROM, where we can write our own interrupt routines. And so this is where interrupt mode 2 comes in. This is the one where we build what's called a vector table, a table of addresses that say, okay, get me a base plus an offset, which is offset. The offset comes in from the device here on this data input, and it goes and jumps there, reads the byte pair at that location, and then executes the routine at that location. So really, this enables the programmer to have any number of keyboard handling routines or special routines, which are all going to happen 50 times a second. So that's what. So we will see some programs running interrupt mode 2. So that's a quick whistle stop tour of interrupts. If you're interested in that whole subject, then do feel free to ask me questions about it on Discord. If I put my Discord into chat, we can have a chat about that. I'm not 100% expert on it, but I do understand enough to have coded the interrupt handling. So, and I say here we are non-masked interrupt. I haven't done anything with, so nothing in our emulation generates this. So that's something I've got to investigate, because there is code in our Spectrum ROM for handling non-maskable interrupts, and to figure out how and when those are generated. Okay, if we go back over here, as you can see, we're going to stay in this while loop until an entire screen is ready. So we're going to stay in this loop here for the best part of 0.02 seconds on the whole. And if I kind of look at the output and how long this elapsed time is per frame or per update, then it is pretty close to 0.02 on my machine. Mileage may vary on your machine. It might be faster if you've got a better machine than me, slower if it's not as good as mine. And that's where you need to tune this figure here, till you get about 50 frames a second on average most of the time. Okay, so what happens then? So then we say, well, have we got any keyboard input? If our window has focus, then if the escape key was pressed, then we're going to do a CPU reset. If F1 is pressed, then we're going to be able to load up what we call a snapshot, and this is a memory snapshot, and I'll show you this shortly. Otherwise, we actually look for other key presses. So there's a method here called update input. We go there. Basically, all this is going to do is try and figure out which key has been pressed, and you can press multiple keys and you can hold them down or tap them. So this will set up a little array called keyline and pass that back. This is quite a long little method. I've also got some helper keys here to activate the delete key and the cursor keys if the cursor keys are used by whatever program running. We pop that back to here, set key matrix here, and then we pass key matrix back to our bus. Update the app name, the window title, so that we've got an output of our frames per second, and then we draw the screen. So basically, we in our bus, which is emulating the ULA chip, we are building a sprite, and then we flash the entire sprite onto the screen. So there's no, in this case, there's no build-up of the image on the screen, and that is limiting. It means it doesn't act like a real Spectrum would have acted, but it's a good way of getting a nice clean transition, so we don't get a lot of flickering. We draw the sprite. So what happens when we've set the key matrix to this array called key matrix? Go over to the bus. The bus is basically emulating the the ULA chip within the spectrum. Okay, so 50 times a second we're calling that interrupt. The interrupt routine is initiating a keyboard scan, and what happens is we send a read peripheral. It's called the in opcode to a certain port, and here the port is any port which is even numbered. Any even numbered port is the ULA. Okay, so there are 16k of ports available. 8k of those ports all refer to the ULA. And what happens is that we look at the high order byte of that port number that got sent in. We ignore the low order byte because that's always going to be something which is an even number. And an even number in the lower byte simply means this is the ULA. So this is why we're saying if we AND a port with 1 and that's a 0, there's a 1 in the least significant bit, then this is you know what I mean. Basically, we've got we are polling the ULA. We work out what key row we're at, and then we scan through. So these are the various values. This is row 7, row 6, row 5, and we're looking what keys were pressed. And remember, a 0 means the particular key was pressed. So we start off by saying, well, no keys are pressed, so all ones, FF is our result. And then we basically reading which keys were pressed, send that back to the interrupt routine. So what effect does that actually have? Well, let's start our emulation. Once again, I press the enter key that time, and I'm getting this flashing cursor. The flashing cursor, the flashing K. The K means I'm in what's called keyword mode, and I have here a printout of that image that I showed you, so I can look at this and figure out what keys to press. So if we go back over here, you can see we've got numbers here which we can do, and then we've got these white keywords like plot, draw, rem, run, rand, return, if, output, poke and print. So those are the keywords, and when we're in keyword mode, pressing a key actually creates the entire keyword. And this means that the basic that we've written is actually pre-tokenized, because even though we see the word print or whatever on the screen, it's actually just 2 characters. So it's quite an efficient way of programming. So you're not storing the letters print. You just do, no matter how long the keyword is, it's just 2 characters to store that. So let's rewrite a program. Let's write a program. I've got a little program here, which just does something a little bit funky, but okay. So if I type 10, and then I want the print command. Sorry, I don't want the print command. I want the poke command. So the poke command on my little cheat sheet here is the letter O. I type O, I get the word poke. Okay. So now what we're going to do is we're going to randomly change the color attributes of the screen. So last week we described how the color attributes are a bunch of bytes which live in screen address 5800 hex for about I think it's 768 bytes worth of color attributes. So the color attributes are the foreground color, the background color, whether it's bright or normal color, and whether it's flashing or not. So we're not going to change the flashing attribute, but we are going to change the other attributes. And we're going to see what happens. In fact, what we're going to do is change the background, the paper attribute. So what we want to do is we want the decimal equivalent of 57FF hex, and that is 2257. I worked this out beforehand. 522527. Then we want the plus. Oh yes, the plus sign. So you can't just press the plus key on my keyboard. I have to work out which key is plus. So it's what's called symbol shift and K. Symbol shift I've mapped to the control key. We've got a plus sign. It must have been terrible to have to work with this, to be perfectly frank with you. Okay, now we want the RND, the random number command keyword. So in order to do this, you notice that cursor there has changed to an L. So we've gone out of keyword mode and we're in what's called letter mode. And this is lowercase letter mode we're in. I'm now going to switch into what's called extended mode. So I'm going to press the shift and the control key at the same time. We now got a flashing E, and now I'm going to type, I think it's going to be Control T. No, it wasn't Control T. Is it Shift T? No. Oops. Control T, no. Okay. Not T. There we go. So shift, control and shift at the same time, just tap those and then press the T and we get the random. So you can see this is a colossal pain. So people must have got used to doing this. I can't believe. It's a bit easier with the actual keyboard in front of you, I guess, but it's a colossal pain to actually do this. And we're going to multiply the random number by 704. So we need the multiplication sign. Let's go into this. Multiplication sign is symbol shift B, and that's multiply that by 704. So that, in the poke command, that is a memory location. So we now need a comma, which is that, and that was symbol shift N, and now we need actually a value to poke into that memory location. So once we're going to get the random again, and we're going to multiply random here by 127. That's our first line of basic. And you can see we've now entered the line of basic. We're back in keyword mode. We're going to type line 20, and this is going to be go to 10. So a 2-line basic program. It's going to simply execute line 10 a potentially infinite number of times. Now the Spectrum doesn't allow you to run an infinite number of times. It actually will stop. If I use the up and down arrow keys, you can see I can move up and down, and I can edit these lines just by over typing, and I can do that easily. But what I'm going to do is I'm going to type letter R, which is the run command. Press return. Clear the screen, and we start getting coloured squares appearing. So I'm going to let this run for a little while. Now, when I first started to experiment with this very short but basic program, this didn't actually do what it's doing now. It didn't colour in each square. It coloured in blocks of the screen. This told me that my emulation was incorrect, and the way I was reading the attribute block of memory wasn't correct. So it's really important to actually exercise your emulation code with programs which are being run through the emulation and analysing the results and seeing if they're correct. And this happened to me several times while I've been playing this last week with the emulator, especially the Spectrum part of the emulation, when you get things that doesn't seem quite right, and that's because you've got something wrong in the emulator, either the Z80 emulation, or in this case of this, it's the actual color attribute reading. So it's working away, and I'm going to leave that running for a little while, because what happens to the screen, there's no prize for this, but if anyone in chat would like to tell me what is happening to the screen and why it's happening as that program runs, it'd be interesting to see what your thoughts are. We're actually running, you can see over here, we're using 132 megabytes of RAM. Yeah, considering there was only 64k of RAM in the original machine, this is pretty horrendous. 132 megabytes to run this, but we are where we are with modern programming languages. We're not running in the most efficient way. So there's an interesting pattern starting to build up on this screen, even though it's poking random colours, random attribute bytes onto the video RAM. There's a pattern starting to build, and say no prizes, but why is there a pattern starting to build, do you think? I actually left this running quite a long time, just to see the colours shift, and it's quite a nice program to watch. This is the kind of thing back in the day. It's probably your first program. You'd probably crack open a personal computer magazine. There was several back in the day, and there would be programs in there for you to type in. You'd type them in, and you'd learn a little bit how your computer worked. Because here we're actually dealing with changing memory locations directly with that poke command. So you're almost more at the bare metal with these older home computer systems. And I think that's really interesting to kind of think about when back in the day, 1980s, 1990s. I think people learned an awful lot more about computer science and how computers actually work through playing with a home computer than you ever do now, because the computers are so complicated under the hood, that they just kind of use programs, applications, or use high-level programming languages, and you don't really learn, unless you dig a lot. You don't really learn an awful lot about bits and bytes and how it all actually works. So can you see it's starting to produce these diagonal lines? You can see here these black squares here, and then there's pretty strong blue diagonals appearing here as well, and there's a red diagonal appearing there, and there's a yellow diagonal starting to appear. And the longer we run this, the stronger that trend is going to get. And the reason why we're getting diagonal lines is because, of course, our RND keyword, our random number generator, is not random. It's only pseudo-random. So we're starting to see artifacts generated by the fact that it's not a true random number. Getting true random numbers is really difficult. Well, I say difficult, you need the right algorithms. There's some very good algorithms out there to produce quite robust random numbers, but this isn't one of them. This is on the lines of it's probably worse than the crand function, because there are a lot better ones now available in the standard library, and also you can use algorithms, quite simple algorithms, which, well, they're simple in that they don't take many lines of code to create. I wouldn't like to understand how they actually work to produce much better random numbers. But here's the pattern starting to emerge, you can see. Okay, let's stop that. Okay, so we've got keyboard input. The emulator can now write a basic program, and we could write programs to really almost any level of complexity. As you see, we have the flashing attributes working now as well. So what happens with that? I'll go over to our simple bus. then what happens here is we have a frame counter, and if the flashing bit is set, so what happens is that every 16 frames it inverts the foreground and background colours. So that's a simple way to get the flashing, and that's actually what the Spectrum did. It simply inverted the foreground and background colours every 16 frames, and that's, I was really pleased when I pressed return on the boot screen and we got the flashing K, because that's the experience that the original users had when they got their machine home, a flashing K. These colours are still not quite accurate Spectrum colours, but they're good enough for me at the moment. Yeah, so this is how we read the attribute table. So I fixed this. This code is the correct code. There's a lot of repetition going on here, but these bit shifts are really kind of fast, so I'm not too worried about them. Okay. When we write to the peripheral, one thing that happens is we can change the border colour. So this border here. The border colour is set by this code. And basically what we do is we read these 3 bits at the end of the data that's sent to the ULA, to the peripheral, and those 3 bits indicate what colour the border is going to be. So let's show you that. So we run the emulator. Now we got keyword there. So if I now press B for border and I say, I don't know, 1, then we get a blue border. A border 6, and we get that. So interestingly enough, the border isn't big enough. So the biggest border is too big. So I need to sort that out, but we won't do that now. It should come down another 2 lines. Okay, so that's the border. I can also do. So let's see if we can do this. OV. Clear the screen. That's not it. Interesting. There we go, flash 1, and I think if I print then I get a flashing black square. So we got control over the display here. Shows you that. The other thing that we can send in that data byte, sorry, is these 2 flags here. So the microphone and the earpiece. Okay. And what happens basically if the ear bit is set to true, then a sound is being generated by the internal speaker, and if it's 0, then no sound. Now, one thing the emulator doesn't do is produce any sounds. I'm still kind of scratching my head about how to get it to produce sounds. The Pixel Game Engine does have a sound and audio subsystem, but if I try to use that, it actually crashes the emulator and crashes in the Z80 code. I'm not quite sure why. And I'm not really wedded to the idea of having to have any audio, but never mind. I may kind of stick to it and work it out. But if anyone wants to do any work on that, submit a pull request. There's actually an issue open in the GitHub, and I'll post the GitHub into chat. There we go. There's an issue open there if anyone wants to help out by having a go at doing the audio. I think we need some kind of audio manager, and synchronization of the audio is the big problem. I'm not quite sure how to do it. Still, there we go. So that's that piece of code. So let's pop over back into the main program here, and you'll notice that here, when we're looking for keys, I've called out two separate keys. So there's the escape key, which is not part of the ZX Spectrum, and also the function 1. And function 1, I've implemented the ability to load a memory snapshot. The file format is called a .z80 file, and currently only supports version 1 of that file format. So, excuse me, any snapshot files which are in version 2 or 3 of the .z80 file standard, I can load them, but they seem to just reboot the emulation. So I'm not quite sure what's going on. That just bears a lot more investigation. I do have some Spectrum games. They're obviously on cassette tape and they're up in the loft, so I can't use them. And I did want to try and load some games, so I thought we'll give it a go. So one of the games is called King's Ransom, which is a text adventure. This is kind of the kind of simplest thing we'd want to try and get running first. It's basically just text. This one actually is what we call illustrated text adventure, and it has pictures. But we'll start off trying to load up King's Ransom, and let's see what happens when we start our emulator. We'll just move across so we see any error messages. They'll appear up in here. Okay, so here we are at our prompt. I'm going to press the F1 key and we're going to load King's Ransom, and it's going to load virtually instantaneously. If you remember when you had your Spectrum and you had your cassette tape player, you would actually type load here. It would say switch on your cassette tape, and then you would sit there, I don't know, for minutes on end waiting for your program to load, and it would tape error anyway, and you have to rewind it and try again. Eventually it would load. But if I press F1 here, we're straight into our program. So the king has been kidnapped by a band of marauding Picts who are keeping you incarcerated in a dungeon of a castle to the north. Your task is a simple one: retrieve the gold that will pay for the king's ransom. Press a key to start. Let's press a key, and here we are. We've changed border colour to this kind of cyan, and it's drawing a picture. It takes a little while to draw it. Now we have a picture of a bridge, and it says you find yourself on the banks of a turbulent stream babbling along the base of a mountain itself. It's crossed by a stone bridge leading east to a dark cave entrance, and we can see the dark cave over here. You can also see an old oil lamp. What now? So we'll say get lamp. This should be familiar to anyone who's followed my my streams on programming the text adventure. So we got that. I don't know if we can type in. Yeah, we can. An old oil lamp. So I'll say light lamp. Positron light. There we are. Oh, we go east. Go east. Now in a blue border. It's drawing the cave. Inside the mountains it's very gloomy. There's a patch of sunlight to the west, and then dim tunnels wind away to the south and to the east. Let's go south. So now we can see a castle. Moat to the east surrounds a fortress of titanic proportions. The tunnel from which you came is north, and a drawbridge crosses the moat from west to east. You also see a dead rat. Now I'm sure that dead rat's going to be important. We'll get the rat. Do it in. So we've got a lit lamp and a dead rat. So you can see this simple text adventure with the nice illustrations. Someone says high definition graphics here. Is working fine. Let's stop that. So I guess we want to get a bit more adventurous. Another game that I've got on cassette tape with Galaxians. So let's see if we can load Galaxians. This is a Space Invader kind of shoot 'em up. So, if you want to know what level, well, I'm starting off level 1, I don't know anything else. 1 or 2 player, 1 player. Okay. There we go, there's some invaders and there's our spaceship. Oh, I could now move this right, I can fire. So you can imagine there's probably really raucous sound accompanying this. But we haven't got any sound. So with Galaxians, rather than just kind of shooting these invaders as they come down, the kind of the USP for it was this, what's happening now, these wings of alien fighters would come down and then we have to dodge them. Let me get hit. And we've been blown up. And we get another spaceship. There we go. So you can see it plays reasonably well. Oh. There we go. So that plays okay. That's a game that if you're any good at playing games you could play. What else have we got? What else do I have? Let me go and have a look, and we'll see what else we can play. So I think you can see that the emulation that we're running, the Z8 emulation that we're running, it's got to be reasonable in that a couple of fairly simple games have actually successfully run. But let's try something a little bit more complicated. Let's try... Okay, we've got one called Castle Master. Oh, let's give that a go. We're loading up. Okay, I'll press F1. We're in Castle Master. Select the character you wish to play. Now this is obviously a very up-to-date title. We can play as the prince or the princess. So we'll press 1. Control options for keyboard. We want to play the keyboard. You can actually play with a joystick, which is fine. But we're going to play with the keyboard. Okay, oh, look at this. We have 3D, kind of. I can't remember exactly how the controls work. There we go. It's extremely slow, and I was pretty sure it would be very slow on the actual game itself. But this is groundbreaking for its day. Now you can see there's a drawbridge there in that castle. There's a moat around the castle. So we're very limited in colours, it's all in green. But there's a door to the castle, there's a drawbridge. And we can kind of... It draws a lot quicker when there isn't a castle in the way and we can walk around the moat. Have a look at the castle from this... Oh, there's something over there, isn't there? There's the castle from this side. So I haven't investigated this much. I can't remember anything about the game, other than that it's very crude 3D, which I thought was quite fun. What else have we got? Let's have a look. We've got something called Dizzy 2. Let's have a see. So we're going to get a bit more. That was reasonably complicated graphically. It was kind of 3D emulation there. Try. This is a kind of a platformer. Well, a side-scrolling adventure, I'd say, this one. There we go, Dizzy. So, let's enter. Start. Here we are. This is our character here. We can make him jump, I think. And there we go, we can walk. There's a gold coin there, look. But if we go into the water, we're just going to drown. So let's have a wander this way. And we get a new screen. Oh, look, there's a chest there. I think if we press enter, got to be in exact right pixel position to do it. We can pick that up. Yeah. Come on. This is one of the problems. Is you've got to be exact. There we go. We picked it up. So now we can walk this way, and we can drop the chest here. We can try and drop the chest here. Come on, drop the chest. There we go, drop the chest. And now what we can do is we can try and jump. And jump up here. And jump up here. And we need to go this way a bit. And we need to jump. Oops. Oh. So accuracy is obviously order of the day here. It's called dizzy because yes, he spins around. There we go. And we've got a gold coin. Eventually. There we go. And then we can carry on to the next screen. So I think you can see that we've actually got a game, and this is a reasonably complicated game. Graphically, it's got lots of things happening. It should be playing raucous arcade music, I guess, but and here we are, and there's something to read here. What's this going to say? We need to be in the right position to do. There we are. There's scroll and quite cutely a scroll and unrolls there and says this legend has it. Bookjaw the pirate is buried here, still guards over his treasure. So that's pretty good. What else have I got to show? Here's one that some people might recognise. So this one caused me a lot of problems to get running. And this is where I found that I didn't have interrupt mode 2 coded correctly on the Z80 emulation. Getting this one to run was a bit of a problem. It does run, it's not really very playable. So let's load this up. So here we've got a couple of interesting features. We've got scrolling text. And this text didn't scroll initially, it just basically stopped on this screen and nothing happened. I couldn't go on, couldn't do anything. And this was a symptom that I'd coded the halt opcode incorrectly. So I had to go and revise my code for halt. As soon as I got that done, we had scrolling text. And this is an example of where basically what's happened is the program is waiting for the 50 Hz interrupt to fire. And basically it advances the characters along according to that interrupt. It's using interrupt mode 2, and that didn't work properly either until I fixed that. So now if I press 0 to start the game, we actually do get the platforms, and there's Donkey Kong kind of climbing up the platforms to the top. There he is, presumably bellowing down at us, and then our character, who is Mario the Carpenter, is going to appear down the bottom. Which you should do. How high can you get? Okay, here we go. There we are, that character here. And I've got to figure out what the... There we are, we're walking along. And that's some oil that's going to come sliding up to us. Barrel of oil that's been... And you can see we're moving really slowly and the screen's flashing quite a bit. I'm going to try and climb up this can't even remember what the keys are. There we go, Q to climb. So we're going so slowly, it's quite painful, and this oil barrel here is going to come and hit us. I don't know if we can jump. Yeah, we can jump, but we still get hit by the barrel anyway. Okay, so this actually does work. We've got lots of flickery, flashy stuff going on. The controls are pretty unresponsive. Not fantastic, but it does work. And the last one that I've got is, I remember this so well, but actually when I came to load up the program, I just didn't know what to do with it. This is called Lords of Midnight, and it's an epic strategy game. And I won't do much with it because it's got loads of kind of weird commands, and there's even a keyboard overlay that came with it. And so let's run this up. Saw the moon prince. He stands at the tower of the moon, looking southeast to the downs of shadows. So this is it's kind of a text-based game. It's got what they pretty proudly call the landscape system. So this is this view here changes. If there's say an army encamped, you'll see the army or encamped here. If there's a fortress or a town or citadel, you'll see those on the horizon here as you're looking out. And here's the woods. Downs of shadows. Here's the downs, and there's woods in the distance. I can kind of go and look to the north. I'm standing there looking north. The down of shadows there. Now look into the forest of shadows. I can look around me. I can change characters as well, so I can now be Rothron the Wise. I'm standing at the same place, Tower of the Moon, looking, so I can play different characters. There's options. The Rothron Wise found guidance. A voice calls, looking for Coronel the Fey. You must seek the village of Kor. He's down and his dawn, and Rothron is utterly invigorated. The ice sphere is quite cold. So this is all about trying to defeat the Witch King, basically. Doom something or other his name is. And yeah. So that's that game. Quite a complicated game. There was actually a prize for solving the game back in the day when it first came out. So I think you can see, if I change this back to King's Ransom, now, our emulation is, the Z80 emulation is working really well. There are still a few rough edges on it, and we'll iron those out over time. But also our Spectrum implementation here, using our Z80 emulator, is pretty good. And it's only a few lines of code, thanks to the Pixel game engine. It's doing a lot of the heavy lifting. So what it's at, it's 560 lines of code. Obviously there's the images in there, and then there's the ULA, the bus or the ULA is about 300 lines of code. No sound. That's the only kind of downside of all this. And we also got the .z80 snapshot file reader here. This is code that I based upon some work of Arjun Nair, and it's pretty good, but there are some parts of it which I've kind of rebuilt, and I've got to figure out why my emulator only works with version 1 files. So one of the things to work out. Okay. What I thought we should do is write a little bit of code, and so let's run our well, let's put this crib sheet away. Right, there we are. Okay, so let's run the test suite and see where we are with the test suite. So let's just run the whole thing. We should get everything passing. There we go, everything passes. So we've got 279 individual tests in here, and then we've got the validation tests, which is about 1300 plus individual tests. If I run this in debug mode, we'll get to see how many tests are passing, none are failing, and how many tests we've got which are not implemented yet. So over here, you can see we've got 34. So 34 unimplemented tests, and you can see here that which opcodes those tests refer to. Now I'm going to ignore DD00, which is a non-existent opcode. It's in there for particular reasons for the fuse tests, and I'm going to remove that test because it's of no use to me. DD84 is the next one here. Wanadza, thank you very much for the follow. That brings me up to my target, so thank you so much for that. Have some Electric Elf hype. This is one of the shaders that we work on the stream. This is one that was created by Pure Snable, who is or was in chat. So that's that one. In order to celebrate, we'll also have some Hyperspatial hype, which is one of my favourites, with our alien buddy Alf. So if you are interested in these things, these are pixel shaders. These are real-time effects. They're not videos and all that. It's been generated in real time. And we'll also have our Alf blasting off. There we go. I love that one as well. That rocket plume is also being generated in real time. Love that. Let's have some Alfs in chat as well. This should bounce around the screen a bit as well. There we go. Okay. So we've got unimplemented tests, and DD84 is the next one in the list. There should all be an FD84 as well. Okay, so these are basically mirrored. Wherever you find here DD BD, you'll find an FD BD. So we're going to, if we implement these, we should better chop these down quite quickly. Okay. So DD84, so let's have a look what that is. So here's a list of operation codes, including undocumented ones. So we're working on undocumented codes at the moment. If you go through a book like Rodney Zack's book, which I've got here somewhere, this is the kind of book I use as a Bible, really. It's Rodney Zack's Programming the Z80. There's so much in here which isn't true. There's a lot of it is wrong, but it's a very good programming guide. It's quite thick, and Rodney Zack is a really good writer, very engaging. That has all of the documented commands in it, but there's a whole bunch of commands of opcodes that the Z80 will respond to, which are unofficial. They were never written down in any guides, and in the user manual for the chip, they're not in there either. So DD, which is this column here, we want 84. DD84, and there'll be a corresponding FD84 as well, as we saw when we looked at those unimplemented tests. So this is add the high byte of the IX register to the accumulator and store the result in the accumulator. And you can see 85 is add the low byte. So we should be able to code these two and the corresponding FD ones, which we use register IY, and we'll have downed 4 tests. Let's have a go at that, shall we? Let's move that off screen for send. So let's go to our code, and we want, we'll just minimize that, and we want the arithmetic and logic section. So here's okay, so here is some code which adds the value of a register R to the accumulator and stores the result in the accumulator, as you can see there. Okay, well, let's grab this piece of code and let's go down to the bottom here, copy it in, and we're going to change the description. We're going to say what we're going to do is we're going to take the value, the high byte of register IX, which is one of our 16-bit index registers. I'll call you Wanna. So I'll disturb you, but we're actually doing unit testing on assembly code. No, we're not unit testing assembly code. What we're doing is unit testing my emulation of assembly code. So yeah, we pass in the machine code, so in this case DD84, and then I've written code in C# which emulates that instruction, and we're going to basically unit testing that my emulated code does what it's supposed to do in terms of all the status flags that get set on the emulated CPU, in terms of timing, how many clock cycles that process takes, all the registers, including the refresh register, the interrupt vector, and also the kind of the weird pseudo registers like register Q and the mem pointer registers, which weren't kind of undocumented features of the Z80. But it's a pretty comprehensive test, and the tests weren't written by me. That's the good thing. The unit tests are part of the X unit framework. These ones up here were written by me, but this one, pass all validation tests. There's about 1,325 tests which are written by the authors of the Fuse Spectrum emulator to test their Z80 emulation. So what I've done is I've taken those tests. They were written in a kind of a file, and I've written a file reader which will extract the test and the expected results, compare them, and give me back the results of that test. So everything should match exactly. So this is enabling me to kind of to move forward really quickly with the emulation. Initially, when we were working in purely TDD mode, I was having to write the tests first. So I wrote about 278 individual tests. Once I got my emulation to a state where all those tests were passing, I was able then to move over to the pre-written tests and use those to validate. Those showed up errors that my original tests were saying were passing, which was really good, because there are features of the code which I wasn't testing. Like I wasn't testing the timing correctly. So I fixed all that, and now what I can do, I'm still working in test-driven development because all the tests are there for me. All I need to do is write the code to make the test pass. So it's really kind of speeded things up. So we are kind of testing assembly code and machine code, but it's actually the emulation we're testing. But it really is down to the exact behaviour of the CPU. In this case, an 8-bit CPU called the Z80. Okay, so we want to add IXH. Call it that. So we no longer need source. We don't need either of those lines. This is simply going to be, we need to get var n is going to be, it's going to be a byte, and it's the high byte of the IX register. So IX, we'll AND that with FF00, and then we'll bit shift it 8 to the right. One's here. Yeah, I'll put B not an N. There we go. Okay, and then I'm going to pass it into the my pre-written 8-bit add function. Now the 8-bit add function here, okay, does the addition. It also works out the flags, the status flags for the CPU. So that's interesting. Unit test emulator machine code. Yeah, it's proved to be quite instructive. I've really enjoyed the test-driven side of it, up to a point. I did want everything to be supported by some kind of test, and most of it is. So all of the operation opcodes are supported now by multiple tests. Where I've still yet to kind of test in terms of formal unit testing is things like interrupts. But I know interrupts are working because if you were with us just a short while ago when I was running Spectrum games on the emulator, Spectrum games require the interrupt mode 1 and 2 to be working correctly, otherwise they just freeze. And I can see that I can now I can play Donkey Kong, I can play Galaxians and all that kind of stuff on the emulator. So I know that that's kind of the interrupts are working, but I don't have kind of supporting unit tests for the interrupts. And I should be able to do something, and I do want to have something eventually. So my add method here, my 8-bit add method, sets all the flags. And some of these are relatively straightforward. There's parity flags get set, all kinds of stuff. But there's also undocumented flags and the mysterious queue register, which is a register which doesn't actually exist in the documentation if you look at the Z80, but it's actually something that we need to account for. Okay, so that really should deal with that. So what we'll do is go back here. There we are. So add IXH. So let's go and add that into our command table. So all I do in order to interpret the instructions is I have these dictionaries. Some people, when they write CPU emulators, have great big switch statements, and that may be quicker. But I prefer this because it gives me the opportunity to do things like having the exact timing of my instructions here, the breakdown in kind of clock cycles and machine cycles. So I do prefer to do it this way, but there is an argument to say a giant switch statement would actually be quicker. Okay, so what we're going to do, I'm going to copy this 886, and the timing's bound to be wrong, but we'll just drop this in here. This will be 84, and it's going to be add IXH. So this is the mnemonic for the opcode, the machine code mnemonic. I do have a disassembler that's built into this, and that works with our debugger, which is a graphic debugger written in WPF, Windows Presentation Foundation, which I can show you later, and it does do all the various disassembly. I don't have an assembler, but I do have disassembler, and that's why we need to put that in there. This is going to be an implied register mode, and it's add IXH. Now I think this list of timings here is going to be wrong, but let's see. Let's run our debug. So now we're going to run that test that we had kind of squirreled away there. So we do get a fail, and here's the results. So the timing, it's expected 8 and he got 19. So I don't know the timings of these undocumented commands. There are some places where you can find it out, but I haven't gone ahead and done that independently. But I trust the implementers of the fuse test that they've actually done that research, and everything else worked. All the flags got set, and the result, the addition, was correct. We're down to 33 unimplemented tests. So let's go and just fix that timing. So a lot of these undocumented ones seem to take just 8 clock cycles. So that'll be that. Oops, that's the wrong one. That's this one we need to do. So it's just 4 and 4. So 4 clock cycles and another 4 clock cycles, that means. So this is, each of these numbers is what's called a machine cycle, and a machine cycle is a variable number of actual clock cycles, and we're running at approximately somewhere between 4 and 3.5 megahertz. Okay, so that's that one. Let's just run the test again to make sure we're all passing. There we go. Okay, failing is 0, so it's working. So in this pass of the development, what I'm simply going to do now is I'm going to copy this, and I'm going to say we're going to do the low bytes. Change those to L's. And here we're simply going to mask the low byte off, and we're not going to do any shifting. That should be that one, and that'll be 8.5. The low byte of the IX register, that changes to an L. Run that again. And this is quite rapid now because we've already written the code to add things together, to add two 8-bit numbers together. So that passed, no problems. Okay, now we can do the same for the FD variant on that. So if I go back to, so DD something is going to be affecting the IX register, or used in the IX register. FD, any opcode starting FD is going to be using the IY register. So it's exactly the same code. Now I can obviously go in, I can tidy this up and make it parameterized and do that, but I'm not going to do that today. That's all from a later date, because we've got our test to help us. So we can simply just copy the code, update it like this, and then once we've got it passing, we can go to our refactor. So the principle of that we're doing to text-driven development is to make the test pass in the simplest way possible, and then we can refactor later. We change this to IY. IY. Obviously, you've got to be careful when you're doing this cut and paste thing. So always eyeball the code to make sure that you've got it correct. So that looks okay. Okay, and we can now grab these two lines of code, which are in the DD instruction table, as you can see here. DD instructions, and we can do FD instructions, which is this one here, and we can paste these in here. They're exactly the same, except we need to change these the mnemonic. What's it doing now? Go away. This is going to be IY, and IY here. And these two are going to be IY, IY. So we run again. So run the test often, obviously. We are, and now we're down to 30. So two of those we're not going to bother with, so actually it's 28. The two we're not going to bother with are for non-existent codes which are being tested for very specific reasons for the Fuse implementation, and they're not relevant to my implementation, so I'm going to be removing those tests. Okay, so what's next? Oh, we should have run that again, sorry. Debug. Okay, so what's next on here? So we've got 8C and 8D, DD8C, DD8D, and similarly FD8C and FD8D. 8C and 8D. Bring our opcodes across. 8C, so add with carry. So this is the plain add, this is the add with carry. So, very simple stuff. So we need to go to the arithmetic and logic, and we need to find the code that we've already written for add with carry. That's over here. So we'll just grab that. So this is very much cut and paste, and you know, I know that it's not what you should do necessarily. To produce the end result, and there will be a phase now when once we've got all the tests passing, of going through and refactoring. So don't be alarmed at the amount of copy and paste that I'm doing, but it's only because what we want is to have each individual command that's being tested, each piece of code being tested, and then when I refactor them and start to make these things more parameterized, and so that there's less actual physical code, that I'm assured that all tests are going to pass. And the codes support me through that process of refactoring, because that's what you need the tests for. Yeah, do the same for low byte. So this is going to be, don't do that bit. And then we can grab both of those. And we can do the version, just use the Y index register. This. I do really appreciate that follow, by the way, Wanna, because that's my target hit a couple of days early, so I do appreciate that. Thank you very much. Okay, that code done. Okay, back over to our instruction tables. This was 8C and 8D. C and 8D going to be add with carry, so the carry flag is being included in the addition, and it should be that. And I'm going to assume it's the same number of clock cycles. And we'll just copy that down to here. This is the version using the Y index register. Change those to Y, those two to Y. We'll check the code. EDC, IY, high and low bytes. EDC, IX, high and low bytes, IX, low bytes. Okay, so let's run our tests again. Evaluate that. Ignore that. No test failing. So we're now down to 26. What's next? So DD9495 and FD9495. So what are those? We go our code list across. 95, so it's subtract. But we could probably have guessed it was going to be subtract. So let's have a look at those. We are benefiting, of course, from the fact that we are reusing all of our addition 8-bit addition and subtraction code. There's also 16-bit additions and subtractions here, and also the binary coded decimal stuff that we do as well. And there's our logical operators. So let's whiz past those. We no doubt have to deal with those as well. Decrement, increment. We did increment last week. Here we go. This is what we want here. So let's grab this. So this is going to be IX high byte. XH. And here we're not going to do that anymore. We're going to say that. Oops. So N is going to be it's going to be a byte, isn't it? And it's going to be IX. We'll mask off FF once again. FF00. It's a 16-bit register, and then we're going to do a bit shift 8 to the right, and then do the subtraction. So because we're into a new operation, we'll test that separately. So this was 9.5, sorry 9.4. So we'll write this in manually. So 9.4 I think it was, wasn't it? 9.4. That's a new instruction. Okay. And we put the mnemonic in, so that's going to be sub A, comma XH. Suck. Sub. There you go. Then we got the addressing modes, so it's going to be implied because we're not actually getting the information. It's all held within the instruction itself. We're not going out to memory and reading instructions or doing any redirects or relative addressing. It's just implied addressing. And the command we're going to run, the function we're going to run is sub A IXH. And then we've got the timing, and that's going to be a new list of integers. And we're going to guess it. I'm pretty sure it's going to be 4 and 4. Right. Oh yeah, there we go. So that's happy. Take some space there. So let's make sure that's running. I really love the confidence that having all those tests there gives you that things are going to work. And when they don't, you know exactly what's wrong. Well, say you know exactly what's wrong, you know where to look. Sometimes it can be quite difficult to work out what the if it says that status flags are wrong, it'll tell you what it expects and what you got. Working out then how to get the right status flags when they're undocumented commands can be tricky. Luckily, a lot of very dedicated people have done a lot of work to figure out what the undocumented features of the Z80 are, and there's an awful lot of stuff out there, and you have to dig a little bit sometimes, but there's some good documents. A lot of them are very comprehensive, but sometimes you have to go to quite obscure places just to fill in the odd gap. The documentation that's been produced for undocumented stuff doesn't cover. Okay, so we can do the same, exactly the same now for the low byte. And that's going to look like that. Don't be shifting anything. There we go. And we can then do the same for both of these. And we can repeat this for the Y register. The high byte of Y. And the low byte of Y. So we cut and paste, so we need to just make sure we got everything correctly. So this is low byte of the X index register. Yeah. Y. That's okay. So we want 95, which is the low byte version. An L. That becomes an L. And we can copy these two lines again, and then we can pop those down into the FD instruction table, which is like the mirror. What was it? 9495. Put those in here. And we must remember to get our X's changed to Y's. Y, and Y. Okay, again. Okay, so now we're down to 22. And now it's 9C and 9D. And this is going to be the subtract we carry, I'm sure. Yep. SBC, subtract with the carry. So if the carry flag's set, then it's an extra 1 that's taken off the value. If it's not, it's unaffected. Okay, so let's do those. What's over here? So subtract we carry. So this is the code we want. So once again we can start off with the high byte of the X register. Remove this code. And we can say that N is going to be byte X, mask off the top of it, and then bit shift it. Okay, so that's that. Let's test that one out. So this is 9C. We need to go to instruction table DD, which is on here. Right. Nine C. No, we'll be lazy and copy this down. 9C. BC. The high byte. Once again, implied addressing SBC. That. And it changes colour to yellow, and where it quickly goes because we have defined that as a func. Okay. Make sure that worked. Yep, so that's okay, no failing tests, and we've got down to 21, so we need to just implement the low byte version and the same code for IY, sorry. So let's do that. And it's quite time consuming, I guess, to write individual functions and not go through and combine them and rationalize the functions into more logical, not logical, but into smaller methods. Rather than lots of little methods, we can obviously build these methods out to cope with any combination of registers, and we've done that to an extent. But what I don't really want to do is to do that before I've got all the tests passing. So that's why we're opting for this very small, discrete methods. One method does one thing, and then we combine afterwards. So this is exactly the same code, except it's dealing with a different register. And obviously we can send a switch in which switches the registers. We will do that. Not today. Okay. Now we'll just code that up. That would be 9D. Low byte of the X index, and then we can replicate those two lines of code down in the FD instructions. So these things like this DD and FD, these are multi-byte opcodes. So unlike something like the 6502 chip, which had 256 opcodes because it was an 8-bit processor, so that's the maximum number of opcodes you can have. With the Z80, they crammed an awful lot more opcodes in by having multi-byte operations, which meant it was a lot more versatile. But it's the more bytes that make up the opcode, obviously the slower the command is. So single byte opcodes are always going to be a lot faster than multi-byte ones. So you can see here that this subtraction is going to take 8 clock cycles to do. Whereas here you can see this one here, this multi-byte instruction, which is subtracting the contents pointed to by the Y register offset by a value D from A and storing A. It's going to take, that's 11, 16, 19 clock cycles, so an awful lot longer than these smaller ones, and the single byte ones are obviously correspondingly quicker, especially if you have implied addressing. A single byte can do an awful lot then. Single byte opcode can do an awful lot because there's no operands either. It always makes it quicker. Okay, so that's all of those. Let's run our debug. I'm passing, so we're down to 18. And now we get A4 and A5 and corresponding FD A4 and A5. So DD-A4, DD-A5. So this is AND. So we're now into the logical operations. The AND, exclusive OR, and OR. And there's also compare. And that's probably going to be about it. So we're getting very close to the end of this phase of the project. And what we've done is in dispersed developing the all the opcodes for the Z80 with building the visual debugger that we've got. That's the WPF application with the built-in disassembler, and we've also built our Spectrum emulation. Very simple Spectrum emulation, just as a way of implementing the Z80 chip, emulated chip, in a real world scenario, so we can actually see things happening on the screen. So if you haven't been with us all for the whole of it, evening Rambling Geek. Actually, Rambling Geek, I think what I'll do, as you only just joined, and there might be some people that haven't seen the emulator running Spectrum games, we'll show you that. So this is King's Ransom. So here we are running a nice text adventure with a bit of graphics in it. and we can say get lamp here. Okay, so we've seen this kind of thing obviously before, but it's nice. It's actually running on my Z80 emulator. I'll just change the. I won't go through all the ones we went through before, but I'll just change it now to do Dizzy 2 because that's quite fun. It loads the games awful lot quicker than real Spectrum. This is a game called Dizzy, Treasure Island Dizzy. You can walk around, you can see. Very interesting kind of graphical things. I'm not sure if he's really supposed to change colour like that. This is very interesting as well. I have to be on exactly the right spot to pick up the items. And here's a drop it. Come on, drop this chair. There we are, thank you. And then we can do a jump. So that's running a bit more complicated game rather than just so you can see the actual music. Interesting, it does a bit of flashing. I mean, you had a Spectrum back in the day as well. I don't know if you remember if the graphics were flashy like this, but I think the trees and the clouds look nice and the rocks. I think it's a pretty decent indication that we've got most of our emulation actually working quite right. Okay, what was that? What were we looking at? It was A4 and A5, which is ANDing the high and low bytes of the index register X with the accumulator. In fact, let's go and do that one then. Out of the way to AND. It's all the code we wrote last week. And just coming up to AND. Yeah, there we are. So we grab this code here. So this is going to be AND IXH as we've done all before. So all this stuff here is exactly the same as we've written just now. So there's a fair amount of repetition when you're coding what's basically the very small units of operation. So this is what your CPU does. It's taking me all this time to write it, but obviously there's microcode within your CPU which actually does these operations, and that's what we're emulating with. So the emulation, I mean, it says you wouldn't know where to start in doing this, but basically all you're doing is taking each individual operation and then writing that in a high-level language. So it's lots and lots of small things, which then when you link them together and you write them one after the other, that's what's producing your emulation. So it's not that hard in that sense, but there are a few little wrinkles which can trip you up. So this is once again, we've done this several times this evening. Bytes going to be IX, and that with 00, and then bit shift it. That should be that. In fact, we're going to take a bit of a punt. We've got our unit tests to support us. We're going to write all of them. This is why I like having these unit tests all pre-written for me like this. It makes it so much quicker to write. That makes it more enjoyable, really, because it's having to write the tests first is all really well. It's a good way of learning test development. If you've got the tests up front, then you really can kind of start motoring through a lot of this stuff. And then when you do hit a problem like your tests fail, that's when it you can focus on just that. You haven't got to worry about all the other code that you have to write, because you know that's solid. Up there. Okay, so this is A4, which is a new instruction. And IXH. Once again, we've got implied addressing modes. This is very simple stuff in that sense. Then we've got and did I call it? And IXH. And then a list of integers. And once again I'm going to have to guess, but I'm going to guess that it's going to be 4 and 4 again. The timing. Do lots of 4 clock cycles for the timing, and we'll fix those up if we fail the test on the timing side. And the low byte. And even though we are kind of doing four things at the same time here, rather than stepping back and doing each individual, our tests are going to tell us if we got this wrong. And there's only very small blocks of code to change and fix. So I'm not too worried about jumping ahead and doing multiple commands at the same time. If they were more complex than AND and OR and add and subtract, then I'll be a bit worried. In fact, the add and subtract, say that more complicated than add and subtract, those were quite complicated commands to write, because the way adding two numbers together is easy and subtracting two numbers is easy. It's the status flags of your CPU you've got to take care of. So there's overflow, carry, half carries, and then undocumented flags which get set or reset. So we're supported by the fact that those functions are already written and have been tested by literally hundreds of individual tests. So we know they're solid. It does happen sometimes though when you start doing undocumented things that really weird status flag settings happen. Some of the ones we've had to deal with the input-output commands have been very, very strange indeed. But because we've got the tests and we know what the results should be ahead of time, we code until our tests pass, and that's the essence of test-driven development, I guess. So that's those. So let's just double check. So we got Y's there, and it's A 4 and 5. And A4 and 5 here, X is there, and X is, that should be fine. So we run our validation tests in debug mode again. And they passed. We now down to 14 tests yet to write. Well, yet to write code to exercise. So I'm pretty pleased with that. So as I'm getting a bit of a sore throat, and I pretty much done what I wanted to do, and I think I'll stop there. I should be able to knock off those remaining 12 to 14 tests really quickly off stream. And I think if Fuel Snable's around still in the chat, I think the plan is that next Monday we'll be doing a shader stream. So it'll be a dual stream with me and Fuel Snable, and we'll look at 2D shaders. So we've done 2D. We started off with a 2D shader. In fact, let's go and have a look at the shaders that we've done so far, just so that if anyone's watching this stream or watching the video that will be on YouTube tomorrow, they get an idea what the kind of things we do on our shader stream. So all our shaders that we've done are up on Shader Toy. So these are the ones we've developed. I can search for them on the stream. Okay, so this is the first one we did, this kind of kaleidoscopic 2D shader. Then we did this one here, which is like a 3D ray tracing shader with all these blobby spheres kind of merging together and circling each other. And we have some nice reflections with this shiny ball bearing rotating around this and merging with the cube. We also did this one here, which is water, and then the kind of the pièce de résistance, I guess you might say, was this one here, which was the fully generated 3D terrain, including forests, ice and snow, water with ripples on it, clouds that move. There was also pools of fog. We've also got shorelines which are being created, and this is all done in real time with mathematics, and the code that does this, all of this, is here, and as you can see it's under 450 lines of code. And all it's doing is doing mathematics. So we're using very, very simple functions to generate this. And I think this is wonderful. So we're going to kind of go back to a shader stream, and we're going to take a fresh look at 2D shaders. We've been into ray tracing and all this, so and we did a bit of text shading as well, but there's still interest to be had in 2D stuff, so we're going to kind of revisit that. So that's planned, hopefully for next Monday. Diary kind of clashes and work commitments on both sides kind of permitting, but I'm pretty sure I'll be up for that, and I think Pure Stable is as well. There won't be a stream on Wednesday. I've still got an awful lot of stuff on in real life kind of stuff on my plate. Hopefully second half of February we should get more back into the normal kind of cadence of 2 streams a week. So there'll be a late Monday stream and an afternoon stream on a Wednesday from about 4 o'clock UTC in the afternoon UK time. So hopefully that should happen soon. But say there's still too much going on in real life at the moment for me to kind of commit to doing 2 streams a week. Okay, so let's commit this to our GitHub repo. So I did undocumented arithmetic and logical codes. So remember, all of this stuff is up on GitHub. Let's just think. Okay, so that will kick off a GitHub action, and that will rebuild all that up on GitHub. Let's go over to the repo. So I'll just pop my GitHub into chat in case you haven't seen it before. Do feel free to go there. So I've got a large number of repos on here, so I've got 37 repos so far. These are kind of the most popular ones. So there's the bot that's running in chat at the moment. If you haven't noticed, we've got a bot in here. Let's have a look at SpaceX rocket launches coming up. So we've got information there. There's a whole bunch of commands, including a full text adventure built into my bot. It's a Slack, Discord and Twitch bot, so that's on Discord here. All of these are free for you to go and use. They're MIT licensed. You can go and download them and do whatever you want with them. I don't mind. We've got our shaders here. We've got our Alexa skill that we wrote is here. The synthesizer, the WPF synthesizer, the bot framework chatbot, AA chatbot is here, and this is the emulator, Z80 emulator. What's interesting, that's the first time I've seen that Twitch badge say live. There we go. And you can see that there's all the code is here, so do feel free to download it. Other stuff we've got in the repo. There's a fork of the Pixel game engine in C# there if you want to look at that. There's our synth, there's a bot. And working on a simulator for the MMix RISC computer by Donald Nuth. Not got far with that, but that's quite an interesting project. But it's kind of running into, it's very similar kind of to the Z80 processor code, so I'll kind of stop that at the moment. There's our shaders. The web API, which started all, this is the very first project we did, build a secure web API using JWT bearer tokens. We've got some work we did in C++ on synthesizers. Wonderful couple of streams here with FuelSnable on T4 templates and how you can use those. A couple of plugins that we created for audio programming streams that we did. F# stuff. This is parser combinators in F#, and other stuff. There's kind of a bunch of stuff there. So do go and check that out. Say the code is there for you to use. There's no problems with licenses. You take the code and you do with it what you want to do with it. It's fine. And if you want to submit any PRs, there's currently one issue here around audio. Trying to get some sounds out of the Spectrum emulation. I do need some help on that, so if you want to contribute, please feel free to do so. My voice is getting very, very dry. Where do I get the launch data from? Rambling Geek. So there's an API out there that provides information about rocket launches. The launches command actually has, so that's SpaceX by default, but you can put ULA in there. For example, it'll come up with a ULA launch schedule. The next one is an Atlas 5 solar orbiter. That got delayed, didn't it? So yeah, so it's come that February 8th. You can also do launches. So there's basically a web API out there which we're calling. There's a NASA launch. Artemis 1. November 1st, 2020. Do we believe that Artemis 1 will take off November 1st, 2020? We'll see. It's actually got there, look. Artemis 3, January 1st, 2024, and Artemis 4, January 1st, 2025. So these are complete guesstimates, aren't they? There's 1st of January each year, so sometime during that year. So, but that's quite interesting. That if you want to look at the code that does that, it's in the bot, obviously, and the SNB bot, and it's very, very simple. Call out to an API, and then you're limited by Twitch into formatting the actual. It's not very nicely formatted. If you run those commands on Discord or on Slack, I think they're a bit better. In fact, let's do that. It's slightly better formatting. At least it's mostly on one line. Yeah. Okay, I'm going to call it a day, I think. Let's find someone to raid, shall we? So who's on at the moment? Raid a channel. So we got the balded bearded builder. It's very hard to say. I think what we'll do is we'll go and raid. We raid Source Scoot. I think we will. Okay, so we'll do that raid. And give him a few more viewers. Do stay with the channel to go and see him. Otherwise, I will see you again next Monday with shader streams. I hope you have a really good rest of the week. So take care, everyone, and thank you for joining me. And thank you very much for helping me achieve 350 followers today. So thank you very much. Bye-bye.